So I got a gigantic whiteboard. And what does one with a gigantic whiteboard do? Well, she makes videos explaining stuff, right? So today we're gonna do something with one of my favorite subjects, organic chemistry. So we're gonna get started with organic chemistry with some main subjects today, which I wrote down right over here. We're gonna cover isomers, then the octet rule and the exceptions to them, resonance, hybridization, alkanes, alkenes, and alkenes, and functional groups. So let's get started with isomers. What are isomers? Well, iso here means similar. Like when you have an isosceles triangle, it means that two sides are the same. So this is a etymology derived word. Iso comes from Greek. It means equal or the same. So isomer means same but a little bit different. So there's two different types of isomers. There's constitutional ones, and there are stereoisomers. As you can tell from the word stereo, it means relating to shape or relating to space, pertaining to 3D space. So these are molecules that are the same but different in terms of stereo space, and these are molecules that are same but different in terms of connectivity. So isomers are molecules that are the same in terms of molecular formula. So they all have the same formula. You know, like when you have the formula of some certain chemical substances, for example, if I'm trying to write the molecular formula for glucose, it would go like this. So that's the molecular formula. So constitutional and stereoisomers are when you have the same molecular formula, but then you have different connectivities. So I can give you an example of this occurring in, for example, let's take 1,2-dichloroethane, okay? Let's write down example. Let me do that in a different color that I'll get from here. Here we go. Let's go with 1,2-dichloroethane. So 1,2-dichloroethane, what is it? So dichloro, so that means there's two chlorines. Eth means that there are inherently, it's going to go meth, eth, prop, bute. So this means it has two carbons, and it's a alkane. So it only has single bonds. So how would we draw this molecule? We have C, another C, and there's two ways you can draw this. One way you might consider drawing this is, since you have 1,2-dichloro, it means that the chlorine is attached to the first and the second carbon. So you might draw the chlorine here and here, and then the rest would be hydrogens, so you don't really have to draw the hydrogen, so it would look like this. Another way that you could draw this, in terms of speculation, is if you have different connectivities. So if it's 1,2-dichloroethane, then it would be named now as 1,1-dichloroethane, because I'm gonna move this chlorine over here, right down here to this carbon 1. Let's number these carbons, carbon 1 and carbon 2. So both of the chlorines will now be on carbon 1, and here one of the chlorines was on carbon 1 and one of the chlorines was on carbon 2. So now that will be different. I'm going to erase that so it's less confusing. And then that was 1,2-dichloroethane. And let's put 1,1-dichloroethane right over here, where we have carbon 1, carbon 2, and we're going to connect chlorine here, chlorine there, and the rest of them are H's. So these are two different constitutional isomers where they have the same molecular formula. If you were to write down the molecular formula, it would be 2 carbons, 2 chlorines, and 4 hydrogens. And here it's the same thing. Let's count with me. Chlorine, 1, 2. 1, 2 carbons. 1, 2, 3, 4 hydrogens. So C2Cl2H4, same molecular formula, but they look a bit different in terms of connectivity. Here, 2 chlorines are connected to 2 separate different carbons. Here, 2 chlorines are connected to the same carbon atom. So they have different connectivities. So that would be something called a constitutional isomer. Now, what is a stereoisomer? Well, a perfect example is 1,2-chloroethane. If we take 1,2-chloroethane, right over here, and if I were to, say, have the same formula, but I move this chlorine, not this time here, but let's say that I move the chlorine to the opposite side, over here. Well, that's a stereoisomer, because now the 3D connectivity, in terms of if I mirror this would have been the opposite, but if I mirrored the other molecule now, it's going to have a translational, it's going to have a transposable axis. That's going to be the difference here. For example, let me draw this so that it's easier to understand. This right here is still 1,2-dichloroethane, but it looks a bit different because this has an axis that if you flip over, it's going to be basically the same molecule. So it has some kind of mirror translatability, whereas this one doesn't. This one actually does, because if you would switch it, it would become the same molecule. And in terms of this, that's why it's the same molecule, but it has different axes of symmetry. And that's why they're stereoisomers. They're quite different, but they're still the same in terms of the molecular formula, because they're still C2Cl2H4. This one has a special name. This one is called cis, and this one is called trans. The one with the opposite chlorines are called trans. Same with the same chlorine on the same side is called cis. So those two are stereoisomers. Okay, now we have covered the topic of isomers. Now we can move on to the octet rule. Octet rule is central to organic chemistry because we're talking about how atoms connect to each other right now, right? In these molecular formulas of dichloroethane, how do we even draw? How did we even know how to draw dichloroethane? Well, let's look at that. Let me redraw dichloroethane. This time, let's go with 1,2-dichloroethane. Let's choose the trans structure. This is actually the more common version rather than the cis because of the steric hindrance, but we will get into that more later. Anyways, this is 1,2-dichloroethane. So how do we know that it's supposed to look like this? Well, we consider the octet rule. The octet rule means that one atom is satisfied when they have 8 valence electrons. That's the most stable version of that molecule. So thus, this carbon atom, if we look at this carbon only, I'll draw like a little circle over it. How many valence electrons does this have? Well, let's look at this covalent bond over here, this CH covalent bond. What is essentially happening over here is this. Hydrogen is contributing one of its electrons because it has 1 valence electron. It's on the first element of the periodic table. Carbon inherently has 4 valence electrons, so it's contributing one of its valence electrons to the hydrogen shell. Now they are covalently, they're sharing this electron. So this electron, carbon's electron, would now contribute to hydrogen's valence shell, whereas the hydrogen's valence electron is now contributing to carbon's valence shell. So now carbon has 1 extra valence electron, and hydrogen also has 1 extra valence electron. Now, this is a perfect example of the exception to an octet rule, because you would think, oh, then hydrogen must still be unhappy because it only has 2 total valence electrons. And I thought the octet rule meant that we needed 8 valence electrons to satisfy it. Well, actually, hydrogen is one of those exceptions. It's hypovalent, hypo meaning low. So it only needs 2 valence electrons to satisfy itself. And there are more atoms like that, such as boron or beryllium, that need less than 8 electrons to satisfy itself. For example, boron only needs 6 total valence electrons, and we'll get more into that later. However, for now, yes, this is a covalent bond where the electrons are shared. Now, carbon is still not satisfied though. Carbon wants how many more electrons? Right now is 1, 2, 3, 4, 5. 5 valence electrons. Now it needs 3 more. And, oh, what is this? It is connected to 3 more atoms. So, if we draw this out, like this, it would now have a total of 8 valence electrons in its spherical hemisphere that satisfy its octet rule. So that is what happens when we're saying octet rule. We want each atom to be stabilized. Now, what about the chlorine atom over here? Well, chlorine has 7 valence electrons inherently. 1, 2, 3, 4, 5, 6, 7. 7 over here. So now it's happy because it has the 8th valence electrons sourced from the carbon's shared covalent shell. So now we've made sure that all the atoms here satisfy the octet rule. And so all atoms are happy. So this is a stable molecular structure. And that's how we know the molecular structure is supposed to look like what it's supposed to look like. That's how you check if that's supposed to be how it is. And now let's move on to exceptions to this octet rule. BAM octet rule. So that means things are going to change around here. Some exceptions to the octet rule include, number 1, as I mentioned, hypovalent electrons. But there's also hypervalent atoms. Not to mention, there are also cases where there's odd numbers of valence electrons. So there are a total of 3 cases, 3 exceptions to the octet rule. The first one being hypovalent electrons. Let's, for example, take boron. Boron is one of those, and when we say hypo, it usually means they only take 6 valence electrons and not 8. And one example of that is boron. Well, we could look at boron tetrafluoride just to kind of examine this a little bit. Boron, let's find boron on the periodic table really quickly. I'll show it up on the screen over here as well. Boron inherently has 3 valence electrons because it's on the 3A column of the 3A period of the periodic table. If we try to draw boron trifluoride, it's going to look like this. And we'll talk more about its molecular structure, how it looks in 3D space a bit later when we get to hybridization in 3D space via CPR. But right now, it has 3 valence electrons. Now, fluorine each contributes 1 more, like this. So it would look a bit like this. Now, boron trifluoride is a known stable substance. It's a known inorganic compound. But if we count the valence electrons for boron by drawing a circle over it, it's 1, 2, 3, 4, 5, 6, only 6 valence electrons, yet it's still stable. So it means it is a hypovalent atom. And let's take, for example, hypervalent. Hypervalent are, oh, by the way, beryllium and boron are exceptions to this. Hypervalent electrons include sulfur and phosphorus, I always have trouble saying that word, which are atoms that will take 10 to 12 valence electrons. For example, we could take, and also we can put XE into that, included in that as well. And this is actually an interesting phenomenon. Why are hypervalent electrons existent? Well, if you go down the table of the periodic table of elements, you'll see that, I'll put up the periodic table here again. Periodic table. As we get to the second row, atoms like phosphorus, like sulfur, and like xenon. Phosphorus is over here, sulfur is right around here, and xenon is somewhere down here. So as we go down the periodic table, what does it mean? The atomic radius is getting bigger. And why is that? Because there's more shells, more electron shells being added to it. For example, let's look at one atom above phosphorus, which is nitrogen. Nitrogen has an atomic number of 7. Phosphorus has an atomic number of 15. Now let's draw out the electron configuration of nitrogen and phosphorus. If we have nitrogen over here, then nitrogen would have an electron configuration of 1s2, 2s2, and 2p3. Phosphorus, on the other hand, has a molecular structure of 1s2, 2s2, 2p6, and 3s2, and 3p3. because it has 15 electrons as opposed to 7. Now, this added 3 means that it has another shell, which means it would have an inherently larger atom. This would look something like this. Just pretend that this is a nucleus with 7 protons, and this is a nucleus with 15 protons, and it would have an inherently larger radius. And what does it mean that it has a larger radius? Well, it means that the electrons are more evenly spread out. Even though this has a stronger nucleus, because it has a stronger charge, it would pull it in a little more. But since it has more electrons spread over a larger space, it means it has a spatially larger bonding space. It has a spatially larger polarizability. We call that polarizability. The ability for the electrons to shift around. And when this happens, we consider this having more abilities to bond, because this electron might be here 1 second and here 1 second, so it has a larger spread over bonding space. It just inherently has more space for atoms to connect and covalently bond with this atom. Thus, it has more bonding space. For example, if I try to bond out of here, as opposed to here, I would have a lot more I can bond with. And that's inherently how to think about this. Now, why is it an odd number of valence electrons in exception? Let's take, for example, a compound like nitrogen bonded with oxygen. When nitrogen is bonded with oxygen, we start off with 2 double bonds here. They have a total of odd valence electrons, because this has 5 valence electrons, and oxygen has 6 valence electrons. We add them together, we get 11 valence electrons. That is an odd number. Now, whenever we draw a formula like this, we first start off with a sigma bond, a single sigma bond, and then we add if we find it necessary. For example, this is necessary for nitrogen and oxygen because they both have a greater number of valence electrons, which means that they can share more than 1 electron with each other. And then we try to draw out the lone electrons. So we have 1, 2, 3, 4 electrons already drawn out. Now we have 7 valence electrons that we have to distribute. Let's say we can do it like 1, 2, 3, 4, and 1, 2, 3. Now, that is an odd number of valence electrons. That is an exception to the octet rule, because you cannot equally assign the electrons. And in this case, there's going to be a resonance hybrid. Sometimes it's going to be with nitrogen, but let me draw it over here. But sometimes the 3 electrons are going to be on oxygen, like this. So there are different times where different resonance structures pop up. This is a perfect segue into our next topic, which is resonance. So resonance particularly happens when there's the same atomic configuration, but there's different electron distribution. And resonance occurs because the electrons are delocalized, and they're trying to find a shifting electronic structure, a structure in which electron distributions keep on shifting. And this is a perfect introduction to resonance. There's an important rule to follow when we're drawing the resonance structure. First of all, the position of first order sigma bonds. The first order sigma bonds, things like, for example, carbon to carbon, and there's 1 bond here, that would be a sigma bond. The difference between a sigma bond and a pi bond is the overlapping of s orbitals versus p orbitals. So this is an s orbital, and s orbitals are always spherical. You can check that out looking at spherical harmonics, but they are always spherical, and the overlap of them creates something called a sigma bond. A pi bond, on the other hand, p orbitals look a bit like dumbbells, and they have it in 3 different orientations in terms of the X orientation, the Y orientation, and the Z orientation. So 3 different orientations. And the overlapping of p orbitals in terms of this would look something like this. Let's say we have another Z p orbital here, and they share electrons like this. So that would be a pi bond. So a sigma bond is way more stable, as you might imagine, and it stays no matter what, which is why the position of sigma bonds do not change. Rule number 2 is that non-bonding electrons are the number of non-bonding electrons will always stay the same. What do I mean by this? The number of non-bonding electrons would essentially mean the lone pairs. And the number of lone pairs will stay the same overall. When I assigned this, it didn't go from 7 lone pairs to 6. It stayed the same in this structure and in this structure. And that is what I mean by the same number of non-bonding electrons. Rule number 3, all atoms must satisfy the octet rule. Obviously, except for the exceptions that we mentioned beforehand, but it must follow the octet rule. And fourth of all, the direction of electron transfer is marked by an arrow. It's marked by an arrow. What do I mean by this? Well, let's actually draw a resonance structure. Let's think of some kind of atom. Let's think of some kind of example. I'll draw one over here. Let me erase this. Let's say we have this molecule where we have inherently 3 carbons. And let's make hydrogen pop up over here, and 2 hydrogens left pop up over here. Okay, this is a beautiful molecule. And we could name this molecule. There would be a more detailed video on this, but essentially we would find the main carbon chain over here, and we will recognize that this is an alkene. We're going to get into that actually right 2 videos after this, but this is an alkene, so it's going to be, it has 2 carbons in this alkene main chain, so it's going to be an ethene. And then it has a methyl group. Oops, I screwed up. That is not a methyl group. Cut that part. Okay, let's say we have a structure looking like this. What do we immediately notice about this structure? Well, this carbon is not going to be happy because all the other carbons have 1, 2, 3, 4, 5, 6, 7, 8. This carbon too, 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. But this lonely carbon only has 6 valence electrons. So this becomes a carbocation, meaning it needs more electrons, so it's electron deficient. So it becomes a cation. Its overall charge is a bit more positive. So when this happens, there's a resonance structure because this bond over here can switch over to the other side. Now, what do I mean by that? It means this can happen. It can go from here, switch over to here. Now, what would that look like? Let me erase this last rule over here because I'm demonstrating it right now. And then we would have something like, let me draw it a little bit downwards. We would draw something like this. And now it means that this carbon is going to be electron deficient. This carbon is not very happy, but now this carbon is. So it switches around because sometimes it's preferred that the double bond is on this side. Sometimes it's better that it's on this side. So that is the resonance hybrid that happens when there's a cross between the two. And you would actually display this when it's a hybrid as looking like this. You would have the sigma bond as a central, and then you have 2 dotted lines showing that it can be either. And then you show the 2 H's connected to it, like this. That would be the resonance hybrid structure. Okay, now we can move on in terms of that. And we can move on to Oh, yeah, we can move on to the major product versus the minor product. Okay, so major product and minor product in resonance structures means what if one structure is preferred over the other? This is not the case for this molecule over here, but there are certain situations where that does happen. And it happens when there are, it's preferred that there are more bonds and less charges. More bonds, less charges. And when there are charges, it's preferred that the negative charge goes to the electronegative atom. And electronegative atoms like oxygen, like fluorine, like chlorine, often prefers to have that negative electron density because they all have either 6 valence electrons or 7 valence electrons, meaning that they would like to get more. It's easier for them to gain electrons to satisfy the octet rule because they only need 1 or 2 more, rather than to lose all of them to get a full, complete shell when they expulse their outer shell. So let's have an example of this over here. Let's say that there's a structure that looks like this. Okay, let's say there's a structure that looks like this. Like this. Okay. Now, these two lone pairs on the carbon can choose to go over here, because right now this carbon has more electrons than it needs. And now this can go over to here and then make sure that that this becomes a double bond, which means that this carbon is now overwhelmed. So this electron distribution goes over here. And now what happens is that the carbon double bond forms here. Let's erase this. This carbon double bond forms here. Oxygen becomes like this. Now it's negatively charged. And CH3, H, like this. Now, this is much more of a major product, minor, because here the negative is on the carbon and here the negative is on the oxygen. This is actually called an enolate ion. And enolate ions are always preferable because it is the oxygen that holds the negative charge, and oxygen is inherently more electronegative compared to compared to carbon. So that is why that happens. So now we are done with covering resonance. Now we can move on to hybridization. Okay, what happens in hybridization? So in hybridization, we are going to be looking at sp, sp2, and sp3 hybridization. Hybridization basically happens when s and p orbitals mix characteristics. And I explained how s and p orbitals look like. This is what s orbitals look like. This is what pz looks like. Py, px. This is how they look like in terms of orbitals. And what if we were to mix their characteristics together? That's what happens in sp hybridization, or sp2 hybridization, or sp3 hybridization. An easy way to look about this is this. Let's take, for example, a carbon atom, and let's take its electron configuration, which is 1s2, 2s2, and 2p2. Now, let's draw out the 2s and the 2p2. The 2s electrons are here, whereas the 2p electrons are a little bit higher in energy than the s orbitals. So 2px, 2py, and 2pz. And following the rule of the Pauli exclusion principle, it is always preferred that the new electrons go into one additional space rather than like this to avoid steric hindrance. And the 2s orbital is stuck here. Now, what happens, for example, if we say that there's some energy provided here, and this electron is now excited and is elevated to this level? well, then the electron structure would look a bit more like this. One electron is promoted up here, and because of its promotion, this electron is carried up over here as well. So then, these two promoted electrons, actually let's do the two promoted in the same color. These two promoted electrons become hybrid orbitals. So these two are now hybrid sp3 orbitals. So there becomes two new hybrid orbitals over here where we have 1/4 of an s character. They are called sp3 orbitals. And they have 1/4 of a character and of s character. And it is important to realize this because you need to know which characteristics have more of one characteristic. And sp3, how you can calculate the p characteristic is it's s1 and p3, right? Then you add the two coefficients together, which makes 4. And then you get the proportion of s above that. So the total s plus p over the s individual. And that's going to be 25% s character. The least amount out of all, which means it has the weakest bond. Because the p bond has a weaker bond compared to sigma bonds, as we learned before, which is why it has a weaker bond. Now, what happens if we move on to higher hybridizations like sp2 and sp1? Well, this just means that less of them are hybridized. So let's take the same situation where we have 2px, 2py, 2pz, and 2s. In this situation, let's leave one of our p orbitals unhybridized. So one of the p orbitals are just going to be promoted to a higher level. When energy comes in, this goes over here and remains unhybridized. Whereas these two atoms are then promoted to take its place over here. We're going to erase this now. And there becomes two new places over here. So inherently, there are 3 sp2 orbitals. Oh, by the way, here there will be 4 sp3 orbitals. 1, 2, 3, 4. Here, there are only 3 hybridized sp2 orbitals, and one of the p orbitals is left unhybridized. So here, if we would calculate it, s plus p over s plus p is going to be 1 plus 2 over 1, so 1 over 3, it's 33% s character. Okay, now we move on to sp1. Now, let me erase sp3 now, because we've looked at that already. sp1 is when there's the least amount of hybridization. So what would happen if there's the least amount of hybridization? Let's imagine that we have 2px, 2py, 2pz, and 2s again. Here, 2 of the molecules are elevated to a higher level and left unhybridized. And these 2 are elevated in their place, like this. So the 2s orbitals are now in this position, and the unhybridized orbitals are up here. So what now happens is that there are a total of 2 sp1 orbitals, and this one, if we use our formula, s plus p over s, 1 plus 1 over 1, there's a half percentile of s character, so a 50% s character in this case. So that is hybridization, and you can use hybridization to find very specific and very helpful things. When we look at a molecule, they aren't always on a flat piece of paper. Molecules don't look just like if I were to draw CC. Let's draw ethane on here. It's not going to look like this on a flat piece of nothing. It's going to have some angles. It's going to have some torsion. It's going to have different bonding orders over here. And that is shown by VSEPR. Valence shell electron pair something theory. I actually don't remember the whole acronym, but VSEPR basically shows how this works. And it's very important to remember the sp3, sp2, and sp orbitals. Because if you, for example, count this carbon atom over here, then you would be able to count, let's draw a circle around this carbon. 1, 2, 3, 4 bonds that are happening. So this adds up to steric number of 4. Now we have sp3 orbitals, right? And what happens when we do s plus p? We get 4. So this is indicative of an sp3 orbital. And sp3 orbitals are always tetrahedral, meaning that they have 109.5 degree torsion for every for every hydrogen or RCR angle. Now this is the same case. For example, let's say it looks like this. Then we have 1, 2, 3 general bonds. So the steric number becomes 3. Now what adds up to 3? S1P2. So sp2 adds up to 3. So in this case, this is trigonal planar, where there's a 120 degrees of torsion. And let's go to the very last. It may look something like this. The steric number is 2. Then we have an S1P1 bond, where S plus P is equal to 2. This is linear with a 180 degrees RCR bond. So this allows you to see, in terms of 3D space, how atoms exactly look like, and that is why it is so helpful. So hybridization is now done. Alkane, alkenes, and alkenes are now very simple, but you just have to define what alkanes and alkenes are. Oh, this got erased. In terms of alkanes, it's always CC single bonds. Alkenes are CC double bonds, and alkenes are CC triple bonds. So in this case, we always think of it as having one base bond, so it's going to have one sigma bond. For this, it has one base bond, one sigma bond, and one pi bond. This has one sigma bond and 2 pi bonds. This is mostly the important things about it, especially if you look at alkenes. It's always going to have a trigonal planar structure because it has a steric number of 3. So alkenes, what's so important about them is that they're going to have pi orbitals that look like this, and they're going to be able to share their resonance like this. So that's why alkenes are so important. And later on, when we get into benzenes and cyclohexanes, we'll be able to look a bit more at why that is the case. But for now, that's all you have to know about alkanes, alkenes, and alkenes. And let's dive right into functional groups. Functional groups are really, 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 really important in terms of naming things, but also thinking about what functionalizations they have. So let's get right into hydrocarbons. Hydrocarbons are the ones that we just explained, things like alkanes, alkenes, and alkenes. And there's one thing that we didn't talk about quite yet. So let's sort this out into 3 groups. There's group A, group B, and group C. In group A, we have hydrocarbons. Hydrocarbons have the aliphatic and the aromatic groups. The aliphatic are the non-aromatic groups, which means they have just straight chains. Aromatic, however, have rings. Rings that you might have seen before that look a bit like this. Now this ring actually has a very special name. And when you have an aromatic group, this is called a phenyl group. So if I say, for example, phenyl cyclohexane, then I might have something that looks like a bit like this. And a hexane connected to a cyclohexane. So this would be phenyl cyclohexane. So that helps you when you're naming things. Now we can move over to something called alkyl halides. And alkyl halides, let me erase this part. Alkyl halides are the B group. They include things like alcohol. They include things like ethers. And when you draw these, they always have a form of Rx. Rx. And our job is to name these X groups. So we can go with alcohol, ether, I think we had thiols. What else did we have? We had amines. We have a few more to go here. We have sulfide. Do we? Yes, we do. We have sulfides. And okay, I guess they're not all alkyl halides. Let's say that this is another group. Let's put this as 0, alkyl halides. And I'll put this categorization under, let's say, CZ bonds, where there's a single bond. CZ sigma bonds. Now for alcohols, there's a functional group of hydroxy groups. So this is an OH group, and it's called hydroxy. And ether looks like ROR. And this group over here, the OR group, is called an alloxy group. This over here, thiols, are ones that look a bit like this. It's when there's an S group instead of the oh, actually, no, that's the other one. Thiols are when there's an SH bond, like this. So this SH group, right over here, that is called the, oh, what was this called? Oh, the Mercapto group. Amines look a bit like R, N, H, H. So it's basically an R NH2 group. And it has 2 lone bonds, of course. And this NH2 group is called an amino group. Sulfides are basically like ethers, but in place of O, there's now an S. Like this. And the SR group over here is called an alkylthio group. So those are the basic things that we have to memorize for the CZ bonds. For the third group, I will erase the frontal one over here. Now we're going to get into some double bond groups. A lot of them are connected. And one thing I'm going to have to remember is the Mercapto group. But if we move on to the CO double bond, CO groups, then we have a lot more to talk about. For example, we have aldehydes. We have ketones. We have carboxylic acid. We have esters. We have, what else do we have? We have amides. And we have acid chlorides. Aldehydes are when the group of CO is at the very end. So it may look something like this. CO is connected to R, and this is connected to an H. So this is when there is an ending to the group. So this whole group, the CO and H, is called an aldehyde group. And this is the common configuration for aldehydes. For ketones, it's the same thing, but when it's an R-R bond, so it's in the middle of some chain. So that would be the carbonyl group over here. Carboxylic acid has a very common configuration, like this. Where it looks kind of like this. And then we have the ester. It's kind of the opposite to the ether, where it now has CO. I stepped on something. RO, R. So it has some structure of a OCO group, like this. So it's more like an OCO instead of a COC. And one of it would be a double bond. And I misspelled that. Amides are the same thing, but except when you have a nitrogen, now it's connected to an O, and then there's an H over here, and an H over here. So let me pull down the thing a bit. Yes, it looks like this. So it's basically an amine group, the amine group over here, the NH2, plus a carbonyl bond. So amine plus a carbonyl is the easiest way to think about it. Last of it is acid chloride, where the C is directly connected to the carbonyl and then a chlorine. And then here, obviously, you'll think of this as a very electronegative and partially electron density heavy group. And here, whatever R is attached here, that would be a great electrophile because it would be very electron deficient if you were thinking of this as a whole atom. So that is it for the functional groups.